Welcome to this video on conducting a hypothesis test with paired means using data using RGuroo. Let's begin. A fitness coach wants to test if a new training program improves sprint speed. She measures the 100-meter dash times in seconds for 8 athletes before and after the 6-week program. Use a 5% significance level and the dataset provided to determine if the new training program was effective at improving sprint time. So here is our data set, and we are going to also be loading that into RGuroo. Before we do that, however, I want to think about the alternative hypothesis in this question. So if you want, you can pause this video, try to formulate the alternative hypothesis, and then unpause it, or you can just keep watching. So remember, with paired data, we only have 3 possibilities for our alternative hypothesis. We could either say that the mean difference, mu sub d, is greater than 0, less than 0, or not equal to 0. But what is mu sub d? What are we talking about here? Well, it is the average distance of the sprint time before training minus the sprint time after training. So it's the population mean difference. And remember, in hypothesis testing, we use the sample mean difference to test whether our alternative hypothesis is true or false. So let me just show you what the sample mean difference would be using the data set. So again, here's my data set. So to find the difference between these paired data, I would take, for example, 12.1 minus 11.7, and that would give me a number. And I would continue on, and I would have 1, 2, 3, 4, 5, 6, 7, 8 differences. So if I take all 8 of those differences and then average them together, that is my sample mean difference. So that is the difference that we're talking about when we refer to the population mean difference. But now let's ask ourselves the question, if the training program was effective at improving sprint time, would we expect this mean difference to be positive or negative? Well, let's think about it. The phrase that is the key in this problem is improving sprint time. But what does that really mean? Does that mean that the sprint time will be longer or shorter after the training program? Well, ideally, if you're running a race, right, you want to be faster, meaning that you actually want to run the same distance in less time. So the time should decrease. So another way to say that is that the sprint time before training minus the sprint time after training should be positive. In other words, it should have taken me longer before I did the training than it did after I did the training. That's the goal. So our alternative hypothesis is mu sub d is greater than 0.
Okay, so when you log into RGuroo, you're going to look something kind of like this. So we're going to come over to the coordinate menu. I'm going to select Analytics, Analysis, Mean Difference, Normal to Population. So the first thing we have to do is select our data set. So this is going to be called sprint time. So the first variable is the sprint time, and then the second variable is after. Okay? So the next thing I'm going to do is I'm going to tell RGuroo that I'm using paired data, and notice that it changes everything down here. It also gives me a summary, right? So I have my sample mean, so remember that's the average distance, difference, right? So there's 8 times, before and after times. Then we have a sample standard deviation and a sample size. Okay? So now, I don't want to analyze population 1 or population 2 by themselves. I want to analyze the difference. So I'm going to come over here. Notice over here, the paired data assumption has already been selected for me. Okay, so we have confidence interval and hypothesis test. I would like to do a hypothesis test. Remember, we already established that the alternative hypothesis is that the average distance is greater than 0, meaning that my running time and the sprint time decrease after the training program. And then I want to select t-stat because I have a really small sample size and the population standard deviation is unknown. So then I'm going to go ahead and put this little eyeball here. Okay. And we go through and search, but the ultimate value that you want is this p-value right here. So, is there sufficient evidence that the process at decreased level to support the claim that the new training program is effective at improving sprint time? Well, here's our p-value, and this might look strange or unfamiliar to you, because 3.15982 to the negative 6. So this is actually something that's called scientific notation. If you wrote it in normal scientific notation, it would be 3.9 if you look at the standard rotation, it would be 0.50 centimeters an hour. So hopefully you can all agree that this number right here is way, 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 way smaller than this particular stuff. Now, scientific notation is something that is easy to, I can put a link to an instructional video about scientific notation in the description to this video, and you're welcome to watch that. But essentially, what we're doing here is we're just moving the decimal place over from here and moving it to the left 6 units. So I'm making here like 1, 2, 3, 4, 5, 6. So that's where the 6 comes from. And as you can see, it's really, 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 really small. So, since the p-value is less than the level, we have to reject the null. So we say that there is sufficient evidence to support the claim that the nuclear program is effective and prevents the claim of the 5% of the interest. So normally, I stop the video here after I have finished my hypothesis test. But I want to make one further point, which is the difference between statistical significance and practical significance. So let me explain to you later. So we said, based on our statistical analysis, based on the results of our hypothesis test, that there is sufficient evidence to support the claim that the training program is effective. Right? However, does that translate into practical significance? So what do I mean by practical significance? Well, if you look at the sample mean, it was less than 1 second of difference. Less than 1 second of difference time. Now, that's okay, because if you go back and look at these numbers, the race numbers themselves, they're pretty small. They're really low. So if I look at the data, we're already down to 12 seconds. So if I go from 12.1 seconds to 11.7 seconds, I can't get that much faster, right? Because I'm doing 100 meter dash, and this is already pretty darn fast. So it might be that these are practically significant, and that these are winning race times. But what if all of the first and second place winners have race times that are under, let's say, 11.5 seconds? Right? So it would be statistically significant, but it's not practically significant, because that means that only maybe this runner right here who ran 11.2 seconds, that's the only runner who is running under 11.5 seconds. So if they're, or this one is sorry, so we can't afford. So those are the only runners who would potentially place the race. I mean, I don't know. I'm not a sprint runner. I'm just guessing. But it's something that we always want to think about when we talk about statistical significance versus practical significance. So just because we reject the null and we support the hypothesis doesn't mean that we have practical utility in your program. So again, we would have to look at the unit base times of what the regular sprint relative to what the races will be won and the times of the people who are placing in the race to answer this question of is this average increase of practical significance? Is it really going to help each runner or team in better